All right, it's 8:30, so let's go ahead and get started today. All right, good morning, everybody. It's our first lecture after the midterm. So how's everyone feeling after the midterm?
Tired.
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 Yeah, I can totally understand. Yeah, so it's so I haven't had a chance to look at them yet, but I plan to grade them before this Wednesday. Oh yeah, I'm sure there were a ton of midterms last week. But so you should know what you'll get by Wednesday. So look forward to that. So I haven't looked at them at all. So I have no sense of what's the average or what's how everyone's doing. So I'll be able to tell you that stuff on Wednesday. Okay? So hopefully at least everyone had a good weekend. After the midterms. I was telling Stephen before the class today that I made homemade chili oil this weekend. So that was kind of how I spent a good portion of my Saturday. Another thing I did was they opened up this like restaurant supply store near me, and that's why I went there. So it was fun to go around. So I've always enjoyed cooking a lot, and they opened this store recently, and I've been wanting to go. But it's funny because this location used to be like a golf supply store. So like, and like after talking to the employees at the restaurant supply, they're only there for about 6 months just to kind of liquidate a lot of their excess inventory. So they didn't bother redecorating. So you have pictures of like Tiger Woods going like this, and like Phil Mickelson and all other pro golfers. But right underneath, you can get like industrial grade juicers at a very reasonable price. So it was a fun experience. I think I'll probably go back and buy some stuff. Okay. So the plan for today is we're going to start a new set of lecture notes. And so the lecture notes we're going to start today is kind of the first part of our control volume analysis. So it'll be kind of like a 4-part series. And each day we're going to be covering a different conservation law. So today we're going to start with the most basic one, which is conservation of mass. And this is probably, the most important one because this is, one that you'll use throughout all of control volume analysis because it gives us kind of so much information. Okay. So before we get started today, are there just any questions on, anything that I can answer before we begin? Okay. So let's go ahead and get started. And so this is, control volume analysis part 1. Okay, so what we're about to embark on right now, I think of it as kind of like almost like the real like meat of of fluid mechanics, at least the introductory one. So over the next few weeks, we'll be spending time doing control volume analysis, and you'll see, that we can actually apply this to a lot of really practical problems. So, out of everything that we cover in this class, this is probably the one that's, is most practical in a lot of cases because it's flexible, and you can apply to a lot of things, and it's not as limiting as Bernoulli, even though Bernoulli, definitely is very strong as well. And then after that, we're going to go over what's called differential fluid analysis, where we're going to cover a couple topics where, again, that kind of forms the backbone for a lot of, more advanced fluid mechanics analysis if you go beyond this class. Right? But we're going to start with control volumes. Right? And kind of the whole basis of the control volume analysis is the topic that we covered last Monday before the midterm, which is Reynolds transport theorem. Okay? And so if you recall, Reynolds transport theorem, which is shortened by RTT, is given by this. So remember, it's something that relates the rate of change of a quantity within a system to its rate of change within the control volume. Okay? So we have dB dt, okay? And this is equal to the integral, or the time derivative of the integral of rho little b dv, okay, plus integral rho b u dot n hat dA. Okay? And this is on the control volume, and this is control surface, right? And so remember from this expression, big B right here, this is our extensive property. So remember, an extensive property is something that depends on the amount of mass in the system. Okay. And so little b right here is the corresponding intensive property. And the way that we obtain little b is we just take big B and we just divide it by the mass. Okay. Right. And then the other thing that we cover is that each of these terms here has a kind of a plain language or an intuitive definition to them. So this first term right here, this is the production or generation term. Okay. Okay. And so if there's any way for our extensive property to be generated within, within a system, that's going to be reflected in that term. Okay. Okay. Our next term is accumulation. And that's to reflect, anything, or if there's any possible way for our mass to be accumulated within our control volume. Okay. Another name for this term that's kind of more practical for our calculations is this is our unsteady term. And then the last term right here is our inflow and outflow term. So that reflects, since our fluid is going to be moving through our control volume, this reflects the fact that, our quantity can move with the fluid and it can come into the control volume at an inflow and it can flow out at an outflow too. Okay. Okay. So the next 4 lectures are basically going to follow the same format. So we're going to start with RTT here. So this is kind of our most general form of RTT. And then what we're going to be doing is we're going to apply this to, different extensive quantities. Okay. And so the list of quantities that we're going to apply to, this isn't just a limiting list too. So you can definitely apply this to a lot of different things. But just for this class, we're just going to go over kind of the big 4 here. And so we're going to do mass. Okay, so that's what we're going to do today. Okay. Next, on Wednesday, we're going to do linear momentum. Okay. Next Monday, we're going to do angular momentum. And then next Wednesday, we're going to do energy. Okay. Right. And so today we're kind of just going to introduce the concept of applying RTT, and then we're going to do that same process over and over again. Okay? But once again, mass is probably the most important one because it kind of affects just so much. Right? All right. Any questions on this? Okay. Okay, so then now let's apply RTT to conservation of mass and see how that changes our expression. Okay. And so for conservation of mass, what we're going to do is we're going to substitute. Okay. And so we're going to substitute for our B values. We're basically going to be specifying them for this analysis. Okay. And so big B is just going to be mass. Okay. And then little b is just going to be 1. Okay. Because remember, little b is just big B divided by mass. And so if we have mass divided by mass, then we just get 1. Okay. Okay. And so the first thing that we always evaluate before we kind of write out the full RTT is what does our production term look like? What is our generation term? Okay. So in this case, our production term looks like this. And so if we substitute mass in for big B, okay, so we have d m cis dt. Okay. And just by conservation of mass, we know that if we have a fixed amount of mass, that's what a system is. Remember, right? So a system defines a fixed amount of mass. Within a fixed amount of mass, we can't produce or destroy any mass within that fixed amount of mass.
So the dm_sys is the fixed amount of mass on the system?
Yes, m mass, m_sys is the fixed amount of mass on the system. And so d dt is kind of like the rate of change of that mass. Okay. And so if we apply that, and then we apply, we let set little b is equal to 1, then we get the following expression. And so we get 0, because we just said that this term is 0 right here. Then we have partial t. Okay. Of rho dv. Okay. Plus cs rho u dot n dA. Right. And so this right here is RTT. For mass. Okay. Okay. And so even though we've plugged in for mass here, all the terms kind of have the same same interpretation. So that first term, our unsteady term, that's you can think of that as the accumulation of mass within our control volume. Okay. And then the second term is going to be our inflow and outflow of mass into our control volume. Okay. All right. Any questions on this? Okay. Okay, so that's kind of the formula expression that we're going to start applying to examples. But I think it's also helpful to take that equation, kind of state it in just plain language. Okay. And so stated in plain language, basically we can say that the only way for mass to accumulate or decrease within a volume the only way for mass to accumulate or decrease within a control volume is for there to be a net inflow or outflow from the control volume. And so just kind of a very quick kind of mental example that you can think of this is that if you have like a leaky bucket, and so the only way for water to accumulate in the bucket is for you to pour water in at a faster rate than water to flow out of the bucket. Okay? And by a similar token, the only way for for the amount of water in a bucket to decrease is that if it's leaking out at a rate that's faster than what you're putting in, and vice and everything kind of in between. So that's all this really states. So I know it's a kind of a scary integral expression, but that's all that's basically saying is this very intuitive thing of, mass can only accumulate if we put it there, and mass can only decrease if we take it away, basically. Okay. Okay. And so let's kind of demystify some of the terms. Okay. And so first, let's look at the inflow and outflow term. And to do that, let's start by recalling something that we learned from our Bernoulli, which is the expression for mass flow rate. And so our formula for mass flow rate looked like this. Okay, so we had an m dot, and we had a rho, we had an a, and we had a u. Okay. And if we go by dimensions, the dimensions for this will be mass over time. Okay. And so just to kind of label these, this row right here, this is our density. Okay. This a right here is area, and this u right here is velocity. Okay. Right. And so if we compare that to our expression here, and so if we look at our inflow and outflow term from RTT, we have the following, right? So we have integral control surface of density times u dot n dA. Okay. All right. And so you can see from this integral expression, we have the exact same terms, right? So we have a density, we have an area, okay? So I know we have d area there, but once we perform that integral, then that area just becomes a regular area, okay? And then we also have velocity, right? And one other thing that I want you to kind of remember from last week is this, how to interpret this, this expression right here. Remember, this is a dot product of the velocity and the normal vector to our control volume. Okay? And so in cases where u dot n, let me do it like this. So in cases when we're evaluating this, this integral at an inflow, right? So remember, at an inflow, you know, velocity is going into our control volume, and our normal vector is pointing the opposite way. Okay, so at an inflow, what we're going to do is we're going to set this, make sure that it's a negative quantity. Okay, so remember, inflows have a negative velocity because the velocity vector and the normal vector point in opposite directions. Okay, and then the opposite is true for outflows. Where in the outflows, you know, you have flow that's leaving your control volume, and then your normal vector is pointing in the same direction. Okay, and so when you have those two vectors that are parallel with each other, you know, this quantity u dot n is going to be greater than 0. Okay, right? And so, you know, if we combine these two things, you know, one way that you can evaluate this integral term that's usually the most more convenient for problem solving is just like this. And so one thing you can do is you can sum up all the mass flows that are leaving your control volume, okay? And then you subtract from this the sum of all the mass flows that are entering your control volume. And so a lot of times, you know, this is a more convenient form, and this is the one you're going to use for problems because, you know, we don't actually evaluate this integral all that often. Okay? Or, you know, what's kind of more accurate to say is that we assume that the velocity is going to be uniform across the entire area. Okay? And so, you know, when we perform this integral, the density and the velocity will just be constants that we can pull out, and then we can just integrate area, and then we just get area from that. Okay? And then when you take the product of density, velocity, and area, then you just get mass flow. Okay? And so if we label this term, the sum of all mass flows leaving CV, okay, and then the other one is true too for the the opposite is true for sum of mass flows in. So that's just the sum of all the mass flows that are entering your control. Okay. And so just to kind of just for completeness, the reason we can make this equation, this you know, this equal sign here, is we assume velocity is constant across the area. Okay. And I'll draw a picture to kind of illustrate what that exactly means on the next page. Okay. Before I do that, are there any questions on this page here? Okay. Okay, so then what do I mean when I say that the velocity is constant across the area? Okay, And so let's just take just a usual pipe flow. Okay. Okay. And so we have flow in a pipe, so we have fluid that's coming in through here. Okay. When I say that the velocity is constant, if we draw all the velocity vectors across this pipe, they're all going to be the same. Okay. Okay. Right. And so when we evaluate this integral, okay, we say that this is like u out. Okay. And so, most of the time we assume that the fluid has a constant density, so we can pull this guy out because it's incompressible. Right? And since our velocity is also constant, it's equal to u out, we can also pull that out of the integral. Okay. Okay. Then all we're left with is just the integral of dA. Okay. And then when we simply integrate dA, we just get the area. Okay. And then we take the product of density times velocity times area, and then we get m dot. Okay. And so that's what we're going to assume, I think, pretty much 99% of the time. Right? But in reality, this actually isn't true, because actually, if you have kind of a cross section like this, what's typical is that the velocity will actually change across the surface. Okay? So you might have a velocity profile that looks like this. So this is pretty typical for pipe flow, where you have kind of a maximum velocity in the center of the pipe, and you have zero velocity at the edges of the pipe. Okay? So we'll learn how to solve these problems in like probably 2.5 weeks to get that velocity profile, because this is kind of how it is more in reality, but we're just not going to assume this most of the time. Okay? So in this particular case, we don't have a constant velocity, but instead our velocity depends on the radius of the pipe. Okay. So again, we'll see this in a few weeks, but for right now, we're not going to kind of worry about it. Okay? But kind of just just for completeness, or if you're thinking about using this analysis for a real problem, and you come across something like this, you would yes, yeah, I'm done. So just we're probably not going to use it in this class, but if you come across a situation like this, you can compute an average velocity. Okay. And so if you have a velocity, we call this like a velocity profile. Okay. Because it shows basically how the velocity in the fluid changes as a function of space. Okay. So if you're given a velocity profile, then the way that you can compute an average velocity is you just simply integrate it, and then you divide by density times area. Okay. And so the average velocity, which will give it the symbol u with a flat hat over its head, okay, is simply equal to rho u dot n dA, okay, and then rho divided by rho a, okay, right? And so for this we're basically leveraging the average value. I think it's called the average value theorem, or like the midpoint theorem, or whatever from calculus. Okay? And so we basically just integrate our entire expression, and we divide by the scalar quantities that we're not finding the average values. So in this case, we're integrating velocity, density, and area, and then if we divide by density and area, then we get the average velocity. Okay? So again, for this class, we're probably not going to use this all too much, at least not for 2.5 weeks. But I just wanted to kind of show you guys how to deal with these kinds of problems in case you wanted to, apply this to something that you're working on for senior design or something else. Okay? All right, any questions on this? Okay. Okay, so let's do some examples just to see how this works in reality. Okay. All right. So we're going to go over kind of three classes of problems. So the first thing we're going to do is we're going to go over examples where the control volume is fixed and it doesn't deform. Okay. And then we'll do kind of moving control volume problems, and then if we have time, we'll go over problems where the control volume is actually deforming. Okay, so let's start with fixed control volume problems. Okay, so in this example, let's say that we're designing the kind of the HVAC system for a confined space. Okay, so let's say you work for a workshop that does a lot of painting, right? So it could be like painting for like metals or something like that. Okay? And if you've ever worked with industrial strength paints before, and you worked in kind of a clean room, that it's very important for air to be constantly circulating so that the paint particles don't float around and kind of make everyone and poison. Okay? And so for these kinds of systems, it's really important for air to be kind of constantly circulating. So for this problem, let's say that the air within this room has to be completely replaced every 3 minutes. Okay. So that's our time window. Okay. All right. And so what we're going to need to do is we need to find out, how much air do we need to pump into this room in order to kind of satisfy this safety requirements. And so let's assume our room is rectangular, or it's like a box, just so we can compute the volume really easily. Okay, so let's say that the dimensions of the room are 10 by 6 by 6 feet. Okay, so it's kind of a tiny room. Okay. Okay, so let's draw kind of a figure. Okay, so here's our room. There's our person inside that we don't want to be poisoned. Okay. Okay. And so to ventilate this room, let's say that we just have a single inlet and single outlet. Okay. Okay. And so in here, we're going to have an inflow of air. Okay, so we have m dot in, and out here, we're going to have an outflow. So we have m dot out. Okay. Okay. And so we know the dimensions of these ports. Okay, so let's say that this is a cylindrical pipe right here, and has a diameter of 8 inches. Okay. And at the outlet, we have a diameter of 4 inches. Okay. Right, and so we want to compute a couple things. Okay. And so first, let's solve for the volumetric flow rate of air. Okay. And the units we want to express this in is feet cubed per second. Okay. And then next, let's compute the velocity, the air velocity at the inlets and the outlets. Okay. Okay. So that's our problem setup. Okay. And so, before we do anything in these kinds of problems, the first thing that we always need to do is we need to draw our control volume. And so remember, we went over a couple, guidelines for that at the end of last class. Okay? But one other kind of important thing that was that's kind of implied, but maybe I should have said explicitly. For this particular problem, we want to make sure that our control volume encompasses kind of everything that we want to analyze. Okay? And so for this problem, it's roughly not too bad, because we have a room that's defined by a rectangular box, and so all we have to do is kind of just make sure our control volume goes around our entire box. Okay? Okay, and so there's our control volume. So it's basically going to encompass the entire box, and it's going to cross the inlet, and it's going to cross the outlet. All right, any questions on this before we start solving? Okay. Okay, so let's first compute the flow rate of air. Okay. Okay, and so first thing, let's compute the volume. And so, the reason I use this symbol V with kind of a cross through it to denote volume, just so it doesn't get confused with velocity. Okay? And so, usually volume in the text you'll see as a capital V, but when your writing is kind of messy, it's hard to tell the difference between a capital V and a tiny v. So I do V with the cross on it. Okay? And so, the volume here is pretty simple. We're just going to take all the dimensions of our box and just multiply them with each other. Okay? So you have 10 feet by 6 feet by 6 feet. Okay, we multiply all that together, we get 360 feet cubed. Okay. 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 And so the volumetric flow rate. Remember what we said was that the air in this room has to be completely replaced every 3 minutes. Okay. And so what that means is that we have to basically put in a volume of air equal to the volume of the room every 3 minutes. Okay, so let's take the volume of the room. Okay. And so the volume of the room is 360 feet cubed. Okay, and let's divide it by the amount of time that we need to replace all this air. Okay? And so we have 3 minutes to replace the air. So in 3 minutes is 180 seconds. Okay, and so we do this division, we get 2 feet cubed per second. And so when we're selecting a pump, or like when we're designing our HVAC system, we need to make sure that the flow rate of air going into the room and coming out of the room is at least 2 feet cubed per second, just to satisfy the safety guidelines. Okay. Okay. Any questions on that? Right. So for this first part of the problem, we didn't have to apply RTT yet. We basically just used the parameters of the problem, and then we kind of went from there. Okay. But to solve for the average velocities, we're going to apply RTT for this. Okay. And so, let's go ahead and write down every single term. Okay. And so, the way that, I want you guys to do these problems, that even, once you kind of get practice with these problems, you can kind of see from the beginning, what terms will cancel out or not. But when we're starting out, what I want you guys to do is to write out the entire expression. You don't have to go from general RTT. At least go from the place where we've already applied the big B and little b. Okay, write out the entire expression and then cancel out terms from there. Just so you don't miss anything, because sometimes it's kind of easy to miss some terms if you're not careful. Okay, and so there's our entire expression, and all this is equal to 0, because remember, mass can't be created or destroyed. Okay. All right, so the first thing we'll do is we'll cross out the accumulation term. Okay, and so just because it wasn't explicitly said in the problem, but we know that since this is kind of something that we're designing for a long amount of time, right? So we're saying that this HVAC system has to be running all the time and always has to be replacing the air. We can say that this situation is steady, and we can cross out that first term right there. Okay, and so anytime you have a steady situation, we can cross out that first term, because we know that no mass is accumulating in the system, therefore nothing is really changing with time. Okay. And then, you know, from here, we can write our inflow outflow term into the form that's kind of more convenient. So we can say it's equal to the mass flow in, which is equal to the mass flow out. Okay. And so if we kind of rewrite this expression right here, we get m dot out minus sum of n flow in is equal to 0. Okay. And so in this case, we only have just one outflow and one inflow. Okay. And so let's actually replace these with their full expression. Okay. And so sum of m dot out is just simply going to be density multiplied by u out times a out. Okay. And m dot in is just going to be rho, density rho times u in, velocity in, times a in. Okay. Okay. Any questions on this before I turn the page? Okay. And so at this point, we can simplify that expression. Okay. And so if we simplify this, we get rho, we just basically move it to one side, u out, a out is equal to rho, u in, a in. Okay. Right. And so this actually gives us kind of a really nice result, which tells that when our situation is steady, okay, so when our situation is steady, like we have right here, then the amount of outflow has to equal the amount of inflow. Okay. So any air that we put into the system has to come out somehow. And then what we can do from here is we can take the density and we can cross those guys out, okay? Because we have the same density on both sides, and we assume that, you know, the flow is incompressible. And we get that u out, a out is equal to u in, a in, okay? And then we know that from our Bernoulli unit that the product of velocity and area is equal to q, which is our volumetric flow rate, okay? And q we've already solved for in this problem just from part A. All right. And so remember, part B of this problem asks to solve for the velocities at the outlet and the inlet. Okay. And so let's use the fact that we know Q, okay, and we can compute the areas because remember we're given the diameters of the two ducts, okay, and then we can solve for U out and U in, okay. And so let's say that we solve this expression for U out, and so U out is going to be Q divided by A out. And so if we perform the, we compute the area and we perform this division, we get 22.92 feet per second. Okay. And so that's the outlet velocity. Okay. Okay. And then the inlet velocity is going to be Q divided by A in, which is 5.73 feet per second. Okay. Okay. And so we can see here that the outlet velocity is significantly higher than the inlet one, and that's because our outlet pipe has a much smaller diameter, and so velocity has to go through there in order to maintain the same mass flow. Okay? Right. And so, you know, the reason we kind of start with conservation of mass here is that we've kind of already been talking about this a little bit through Bernoulli. And so, you know, the RTT expression for conservation of mass, a lot of the times it just kind of breaks down to what we learned in Bernoulli, where, you know, mass flow in has to equal mass flow out. Okay? It's just that the only difference now is that we're working with kind of a more general expression where we can deal with kind of multiple inlets, multiple outlets, and we can actually deal with kind of unsteady situations, which is the next example. Okay? All right, any questions on this?
So you're doing the area of our outlet stuff. Are you taking like a cross sectional type area
Yeah.
of that, right? So like pi over 4 times d squared or something like that.
Yes. Yeah. So the area is always going to be whatever is a cross is the cross section for the flow. So whatever the area that's perpendicular to the flow direction. Yeah. Yeah. You can kind of think of it as the area that the flow must cross in order to enter the control volume.
That Q is constant, correct? It's the same one that we just solved earlier, which was
Exactly.
2.
Yeah. So that Q is constant is the one that we solved for in part A. Okay. All right. So that's kind of the basics on how to do RTT for control volumes. Okay. And so now let's start to look at a little bit more interesting situations. Okay? And so first, let's look at an unsteady situation. Okay? And so now we're going to do a problem where that first integral, the one with the partial derivative with respect to time, that one's not going to be 0. Okay, so let's do an example with that involves kind of a road construction. Okay? Something that everyone is familiar with and everyone that gets collectively angry at because it causes lots of traffic. Okay. But let's consider a case where you have workers that are working alongside the road, but they're working in a trench. Okay. Okay. So let's say that we have our trench that looks like this. We have our construction worker. I'll give him a hard hat because he's a construction worker. Let me make it orange. There we go, for safety. Okay. And so what tends to happen for these trenches that work alongside the road is that, because cars are constantly driving past, the cars are emitting, they're emitting a lot of stuff, but the main thing that they're emitting is CO2, right? So you have carbon dioxide that's kind of constantly coming out of cars. And what tends to happen, because since CO2 is more dense than air, right? And since we know from hydrostatics, if you have a more dense fluid, it tends to sink, right? You constantly have this kind of inflow of CO2 that's coming into the trench, just like this. And so, what's done in a lot of practical cases, you might have seen these before, is that there's a hose that's actually inside the trench. Okay, that might look something like that. Okay? And so a lot of times, these hoses aren't actually putting anything into the trench. What they're doing is actually sucking things out of the trench. Okay, and so they're actually sucking in a lot of these. They're sucking out, the CO2 or whatever other harmful gases that are in that trench, just so that to keep the workers as long as in relatively good condition. Okay. But in this problem, we're going to pretend that we don't have the hose, so we have kind of a very unsafe situation, okay. And we want to find out basically, at what point are things going to become unsafe for our worker? Okay. Okay, so just like before, let's draw our control volume. So our control volume will look something like this. So it's just going to surround the trench. Okay. Okay. And let's give our trench some dimensions. Okay. And so let's say that this length right here is 10 feet. Okay. This dimension right here is 8 feet. Okay. And we'll also say that it has a depth of 5 feet going into the page. Okay. Okay, and so let's solve for the following quantities. Okay, and so first let's solve for the rate at which CO2 is entering the trench. Okay, or the rate at which the height of CO2 in the trench changes with time. And so in part B, the time it takes for the height of the CO2 to reach 6 feet. Okay. And so the reason that number is significant is that that's kind of the average age of construction, or average height of construction workers, sorry. And so, this is important to know where, if you don't have proper ventilation, you kind of think of this as the amount of time that workers can work in the trench before they have to kind of circulate all the air out of there, okay? And I know, I know none of you guys have kind of met me in reality, but, this doesn't affect, or this doesn't apply to me because I'm only 5'4", so I would drown in CO2 before this time would actually be computed. Okay. All right. Any questions on the problem setup? Okay. All right. So let's start with part A. Okay. And so part A, we want to find out the rate at which the height of CO2 is changing within the trench. Okay. And so let's apply RTT. Oops. Okay. And so again, we're going to write out the entire expression. Okay. So we have 0 is equal to partial t of integral of rho d volume, okay, plus integral of rho u dot m dA. Okay. Oh, I forgot to give one more thing for the problem. So we need to know the actual inflow of CO2 into the trench. Okay. Okay. And so let's say that Q in is going to be 10 feet cubed per minute. Okay. All right. And so in this particular problem, since we're saying that CO2 is accumulating within the control volume, because let's assume that we start with no CO2 in the trench, and then over time, CO2 is going to enter the trench and it's going to accumulate. Since we have this accumulation here, we need to keep this guy right here. Okay. And so let's kind of rewrite this expression and let's kind of simplify it a little bit. Okay. And so the first thing we'll do is we'll say that, we'll apply our usual assumption that the density is going to be constant. Okay. And so if we have a constant density, we can pull them out of the integrals. Okay. And so we have 0 is equal to rho partial t of integral dv. Okay. And then let's replace this expression with the one that we know in terms of the mass flows. Okay, so we're going to have sum of all the mass flows out minus sum of all the mass flows in. Okay. All right. And so first thing we'll do is we'll cancel out the inflow term because, we're going to cancel the outflow term. Because we're saying that the CO2 is just accumulating within the control volume, so there's no hose that's kind of sucking the CO2 out. Okay. And then if we evaluate this integral right here, this is just the integral of d volume. So the integral of d volume is just going to be volume. Okay. And so if we apply the time derivative of that, then we simply get. We get 0 is equal to rho dv dt, okay, minus m dot in. So we just have one inflow in this case. And our inflow is given by this volumetric flow rate right here. Okay. So there's going to be density times Q in. Okay. All right. And so the next thing that we're going to do is we're going to cancel out the densities. Okay. because density is constant, and we can just pull it out and just subtract, okay? And we get dV dt is equal to Q in. Right? Okay. And so what we're saying is that the rate at which the volume of CO2 is changing within the control volume is equal to the rate at which CO2 is entering the control volume. So intuitively, you know, that makes kind of a lot of sense. Okay. All right. Okay. But we don't want the rate at which volume is changing in the control volume. We want the rate at which the height of CO2 is changing in the control volume. Okay? And so what we're going to do is I'm going to substitute, since we have a rectangular trench right here. So instead of the volume, I'm going to say this is equal to the product of the height, length, and the width of the control volume. Okay? Okay. And then after that, what I'm going to do is I'm going to take the length and the width, and I'm going to pull that out of the derivative. Okay? Because since we know from the problem that since CO2 is really dense, what it's going to do is it's going to come into the trench and just kind of spread equally around the bottom. Okay? And so, you know, the length and the width is basically going to be always constant with time, because the CO2 is just going to come in, it's just going to settle, right? And so the only way for CO2 to accumulate is for the height of the CO2 to raise. Okay? And so it's the same thing if you kind of fill a bucket of water, right? So if you fill a bucket of water, you know, you have a kind of a wide area like this, and you put water in, and it kind of spreads evenly across the bottom. And then as you add more water and more water in there, then the level of the water in the bucket is going to raise. Okay? And so this is the same thing with CO2. So that's why we can say that the length and the width of this trench are not going to be changing with time, but the height of the CO2 is going to be changing. Okay? And then what we're going to do is we're going to solve this expression for this dH dt right here. Okay? All right. Any questions on this? Okay. And so if we solve this expression for dH dt, we get dH dt is equal to Q in divided by the length and the width. Okay. And so if we plug in all the numbers, because we have all of them from the problem, we get 0.2 feet per minute. Okay. Okay. And so if we dig this trench kind of in the you know, in the middle of the night, you know, no cars are running, and then as soon as cars start driving past that, you know, the height of CO2 in that trench is going to be raised at 0.2 feet. Okay. And so now that we have the rate at which this height of CO2 is changing within the control volume, we can compute the time. Okay. And so remember, we want to compute the time it takes for the height of CO2 to reach 6 feet. Okay. And so all we're going to do is we're going to take 6 feet, okay, divide it by the rate. Okay. So you have 6 feet divided by 0.2 feet per minute. Okay. And so the 2 feet are going to cancel out, and we get 30 minutes. Okay. All right. And so if we start with basically just an empty trench, no CO2 in there, you know, we start building in the dead of the night. And then as soon as cars start going past, you know, workers can only work in there 30 minutes before it starts to get really dangerous and they're kind of drowning in CO2, which is, you know, obviously not good. All right, any questions on you know, how we plug these guys in?
Seems like a good exam question to me.
Could be. It could be. Maybe a twist on this. Okay. And so, you know, the big reason I wanted to do this problem, you know, first of all, just to kind of give you guys a taste of, you know, how you do unsteady problems. But also just to kind of highlight just the general fact that when you have an imbalance of inflows and outflows, okay, and so that's exactly what we had in this case. So we had an inflow of CO2 but no outflow. Okay, so we're just putting fluid in, but none of it's coming out. Okay, and so when you have this kind of imbalance, this leads to accumulation. In this case, accumulation of fluid within the control volume, or the opposite can be true, where it can lead to a decrease in fluid. Okay. Or in other words, the term that you'll see most often is that this leads to unsteady situations. Okay? So an imbalance of inflow and outflow will lead to kind of unsteady, problem-solving situations. Okay. So those are two examples for one for a fixed, one for a steady problem, one for an unsteady. And so now let's look at problems where the control volume is actually moving. Okay? So we touched on this kind of briefly at the end of last lecture. Okay. And so, you could have situations where it's actually computationally more convenient to have the control volume move. Okay. And so in these situations, leaf blowers here, what we need to do is we need to replace our velocity term in the inflow-outflow term with a relative velocity. Okay. And so our relative velocity, we'll call this W. So this is going to be U minus VCV. Okay. Where this right here, this is the velocity of the control volume. Okay. And so if we plug that into our expression, we get the following. Okay. And so we can still have our unsteady term. Okay. So that's unchanged because we don't have a velocity in there. Okay. But what does change is our inflow-outflow term right here. Okay. Okay. And so for our normal kind of stationary control volumes, all we have in those cases is just this velocity right here. Okay? But when the control volume is moving, we need to take the moving control volume into account. And so we have the difference between the fluid velocity and the control velocity. So this right here, this is our relative velocity. Okay. And so next we're going to do an example just to kind of show you guys how this is used. Okay. All right. Any questions on this page? Okay. Okay. So let's do an example. And so let's say that we have an airplane that's moving forward at a speed of 971 kilometers per hour. Okay. And so what we want to do, and what we want to do for this problem is we want to look at the airplane engine. Okay. Okay, so let's say that an observer on the ground and so the reason I say he's on the ground because this is you can kind of think of it as a fixed reference frame. Okay. Somehow, let's say that he has he's Superman, so he can see things really, really far. That and his eyesight can perfectly quantify the velocity that's coming out of a very fast-moving airplane. So let's just say that he has superpowers. Okay. Let's say that he observes the gas. Okay. He observed the gas that's leaving the airplane engine has a velocity of 1,050 kilometers per hour. Okay. So let's draw our control volume here. Okay. Okay. So here's our airplane engine. Okay. And let's say that it's moving to the left with a velocity of what's given up here, 971 kilometers per hour. Okay. And so in this problem, we're actually going to have a changing density because this airplane's moving so fast, and we're actually going to see some of the effects of compressible flow. Okay. And so at the inlet over here, okay, so this is the inlet. Let's say that we have A1 equal to 0.8 meters squared. And we have the density at the intake here equal to 0.736 kilograms per meter cubed. Okay. And then at the outlet, we have the following stat. So A out is going to be 0.558 meters squared. Okay. We have density at the outlet. This is going to be 0.515 kilograms per meter cubed. Okay. And then we know from the problem that velocity at the outlet, U2, this is going to be 1,050 kilometers per hour. Okay. Okay. And so in addition to these guys, we actually have one more inlet. And so this is kind of our first introduction to kind of a multi-inlet problem. Okay. Is that in addition to the air that's kind of naturally flowing through the air engine, we also have an injection of fuel. Okay. And so fuel is going to come in through this little duct right here. Okay. And it has a certain mass flow rate. Okay. Right. And so in this problem, we're going to use conservation of mass. And since our airplane's moving, we have a moving control volume. And what we want to solve for is the mass flow rate of the fuel to kind of satisfy all these conditions. Okay. And then one other thing, since this airplane is kind of just flying at a constant velocity, we're going to assume that the problem is steady. Okay. All right. Any questions on the problem setup? Okay. And so, let's start this problem the same way that we started all the other ones. So let's start with Reynolds transport. Okay. And let's write out every term here. Okay. And so we have partial t of integral of rho dv. Okay. Plus our inflow outflow term. Okay. So we have rho cs of, remember we have a moving control volume, so we have to take that into account. Okay. Okay. And all this is equal to 0. Okay. All right, so the first thing we're going to do is we're going to cross out the first term right here because we have a steady situation. Okay. And so if we have a steady situation, then our total mass inflow has to equal to our total mass outflow. Okay. Okay. And so let's rewrite this term like we usually do. And so this term is just going to be sum of mass flows out minus sum of mass flows in. Okay. Right. And so if we write this out, we have m dot of the exhaust. Okay. So our exhaust here is our only outlet, so that's the right side of our airplane engine. Okay. Okay. From that, we're going to subtract the mass flow rate at the inlet. Okay, so that's the conditions at location 1. Okay. And then from that, we're going to subtract the m dot of the fuel, which is ultimately what we're going to be solving for. Okay. Okay. And so let's, since we have the, the statistics of the flow at the exhaust and the intake, let's replace these with, let's put these in terms of those quantities. Okay. So m dot exhaust right here is going to be rho 2, A2, U2, or not U. Okay. In this case, it's going to be W2. Okay. Because since we're doing a moving control volume problem, we have to use the relative velocities. Okay. From that, we're going to subtract m dot intake. Okay. And then we're going to subtract the same things at the intake, or m dot fuel, sorry. Okay. Okay. And so the question now, we have, we have the densities of the fluids at both cases, at both the intake and the exhaust. We have the areas. Okay. So now the question, and this is kind of the trickiest part to doing moving control volume problems, is what do we plug in for these relative velocities? Okay. Okay, so let's start with W1. Okay, so W1 is the relative velocity of the fluid at the intake of the control volume. Okay, and so let's go back to our figure right here. Okay, and so it's not really stated here explicitly, but you remember what's happening is that this airplane is kind of flying through the air at this velocity of 971 kilometers per hour. Okay, and so what it's doing is that it's kind of since it's moving, it's basically colliding with all the still air that's in front. Okay? And so we didn't have a U1 right here because U1 is actually 0. Okay? Okay. And so since U1 is equal to 0, we have still air, then what's basically happening is that this control volume is basically colliding with still air right then. Okay? So even though the air itself doesn't have any velocities yet, the fact that our control volume is kind of colliding with that air it's like we have an inflow velocity because our control volume is kind of, it's kind of like Pac-Man, right? So from, Pac-Man kind of goes like this and eats all the little, food in its in the game, right? So the food itself is not moving, but Pac-Man himself is moving. So it's like there's an inflow of food, going into Pac-Man. And so this is kind of the same thing right here. So even though the air in front is not technically moving, it's still air. The fact that we're kind of like sprinting, really fast and moving really fast into that air has to come into our control volume. So that's basically the case here. Okay? And so since U1 right here, U1 is simply just going to be, or W1 is just going to simply be velocity of the control volume. Okay? And so this is going to be 971 kilometers per hour. Okay. And so if you want to plug in the numbers for this, we know that W1 is equal to U1 minus VCV. Okay. And so U1 is equal to 0. Okay. And so we just have a minus VCV. Okay. But since the velocity of the control volume is going to the left, right? And we have the positive x-axis that usually goes to the right here, okay? Then we're going to plug in a minus 971 kilometers per hour, okay? And so that gives us a positive 971 kilometers per hour, okay? And so I think, the most confusing thing for these moving control volume problems is going to be the signs, okay? And so with the signs, you really have to be kind of, diligent when you're applying this formula. You have, velocity of the fluid minus the velocity of the control volume. And you have to make sure that velocity of the control volumes respects kind of the positive x-axis for whatever you're working with. Okay? So in this case, we have a 0 minus VCV, but since VCV was negative, we have two negatives that cancel out, and we get a positive 971 kilometers per hour. Okay. Okay. Any questions on that?
Yeah. So is your U equation U1 minus C VCV is equal to negative VCV?
Yes.
Or is that just a continuation of the?
It's just a continuation because U1 is equal to 0 in that case. And so we have 0 minus VCV, which is just VCV. Okay, so that's W1, so we can go ahead and plug this guy in. And so let's compute W2. Okay. And so W2 is just going to be the same thing. Okay. Okay. So we have U2 minus VCV. Okay. And so we know U2 from the problem. So U2 from a fixed reference case is going to be 1050 kilometers per hour. Okay. Okay. And then the same thing, we're just going to subtract a negative 971 kilometers per hour. Okay. And so if we just perform that arithmetic, we get W2 is equal to 2021 kilometers per hour. Okay. Okay. And so now that we have W1 and W2, we can compute m dot fuel. Okay. So go back to our previous expression. We have m dot fuel is equal to rho 2 A2 W2 minus rho 1 A1 W1. Okay. We plug all that in. We get 9,100 kilograms per hour. Okay. But there's one thing I want to address because I know that, when you guys look at this problem again, there's going to be some questions on this. Okay. And so, let's say, but wait. Okay. And so, we have to think of the sign of U2 right here. Okay. And so U2, I think the question is always going to be, what do we choose for the signs for all of these velocities right here? Okay. And so we know that VCV is always going to be, that respects the sign conventions. and U2 is also going to respect that same thing. So you want to make sure that you pick a sign for U2 that kind of respects that, that direction. So that's what you would think, right? But this U2 and U1, okay? Okay. And so the signs that you pick for U1 and U2, you know, the sign that you pick for that doesn't respect the positive x-axis kind of as we usually do, okay? And so remember, the signs that you pick for U1, U2, the way that you pick that is whether it's going to be an inflow or an outflow. Okay. And so in this particular problem, U2 was going to the right, which is positive x. So in this case, you know, they lined up. But, you know, especially once we get to momentum, we're going to look at cases where, you know, what the sign that you choose for U2 is going to be really critically important for the problem. And in those cases, you just have to respect the fact that it's an inflow or an outflow, and that's how you pick the sign, okay? And so in this case, we picked a positive sign for U2 because it was an outflow to our system, okay? And it just so happened that it was also in the positive x direction. But, you know, I want to kind of just mention it today so that once we start doing momentum on Wednesday, you know, you'll kind of remember this kind of thing. So we're going to have to play with the signs quite a bit, and the signs are kind of by far the most confusing things about these problems. Okay, any final questions on this? Okay, so that's all we got time for today. And so when we pick this up on Wednesday, we're going to start going over conservation of momentum. Okay? And so if you look at the lecture notes, you'll see that there's also a section for deforming control volumes. But since we didn't get to it, you know, I'm not going to test you on it. We might come back to it if we have time on Wednesday, but I think last year I skipped it too because we just didn't have time. Okay, so thank you guys for coming today. Hope you guys have a good rest of your day. Wednesday I'll have your midterms graded, so we'll talk about it by then. Right, and I'll see you guys on Wednesday.
All right, thanks, Professor.
Thanks, guys.
Thanks, Dr. Tran.
Yep. Yeah, sure.